Okay, so you see my screen and you can hear me, I guess, right? So today, our plan today is to figure out how the interrupts are actually, how the interrupt processing is implemented in the x86 operating system. So we will specifically look at the source code first for the same timer interrupt, and then we will cover how the system calls are implemented as well. So just, and today we're gonna assign a homework 4, which will ask you to implement a new system call in the x86 operating system. So that will be the first time where you guys will be working with x86, right? And subsequent homework assignments will be also on x86. Typically, they will be extend x86 with something, so kind of implement a feature. And the idea here that you will be that will force you to look at the x86 source code and like understand it better, read parts of it, and work with it in general. Um, okay, so let's get started. So the idea is just to remind you that we are still looking at the interrupt processing path, which kind of looks like this. So like for generality of the argument, let's assume that we were executing inside the user. So your instruction pointer was pointing somewhere in the user process. Your stack pointer was like somewhere over here, right? That's the values which the CPU had, this physical CPU. And suddenly, remember this fetch, decode, execute loop. Instead of like incrementing EAP by the size of the last instruction and jumping to this next instruction pointer somewhere over here in the user level, the hardware says, okay, by the way, I see that an external piece of hardware, like a timer, for example, wants to raise an interrupt, right? And at this point, the hardware, instead of like moving to the next instruction pointer, what it does the following. It says, okay, look, I have a specific hardware register, this IDT register, IDTR, which has a pointer to the interrupt descriptor table in memory. This table is configured by the operating system. Last time we looked at how x86 does it. So it's just essentially an array. And we just, for each element of the array, which go from 0 to 255, we set some values, and these values have meaning for the operating system, right? And so essentially the hardware just blindly says, okay, look, the timer tries to raise the interrupt number 32. So the hardware says, okay, I know where the interrupt descriptor table is in memory. I know that it's interrupt number 32. So I will pick the 32nd element of this array, and I will do the following. So first of all, I will try to locate the next instruction point, or like something what I have to execute. And this element of this array will contain a pointer to the entry point of the interrupt vector. So in our example, it's vector 32, right? So typically not typically, yeah, okay. You cannot say always, but in most cases, this vector is sitting inside the kernel address space. The user cannot access it directly, but when the hardware raises this interrupt, the hardware loads this address of the handler in the instruction pointer. But however, in order to do this transition, a couple of things have to happen. First of all, since we were running inside the user, our current privilege level was 3. We were running in user. So the hardware will take the code segment value from the interrupt descriptor table from entry number 32 and figure out, like, the code segment is treated as a pointer inside the element inside the global descriptor table. And in case of x86, it will point to the kernel code segment. So this segment will have descriptor privilege level 0, and this is why the hardware will transition from privilege level 3 to privilege level 0 to kind of start running with kernel privileges, right? And since we cannot we don't trust the stack value, we don't trust the value of this instruction pointer, of this stack pointer, which is controlled by the user, and the hardware cannot save the old value of the instruction pointer here on the stack. What it does instead, it says, okay, I will locate the kernel stack. The kernel stack itself is pointed by the element in the task state segment. another table which is maintained by the hardware. It's pointed by the TSS register. TSS specifically chooses a value inside the global descriptor table, and the global descriptor table will have a base of the TSS table in memory, right? And so these two values, the stack segment and the stack pointer, are loaded in the ESP register, and the stack segment is loaded in the CPU register, stack segment register, and the hardware saves these 5 pieces of information on this new kernel stack, right? So one interesting observation that each process in x86 will have 2 stacks: the user stack, which it uses in ring 3 when it just runs user applications, and the kernel stack, this one, which it uses in ring 0 when it runs in the kernel, when either the interrupt preempts the execution of the process or when the process enters the kernel with a syscall, with a system call. And the hardware saves these 5 things: the stack segment, stack pointer, eflags register, because eflags contains the bit which interrupt flag bit, which controls whether further interrupts are enabled, code segment, and the code segment register, and the instruction pointer. So this instruction pointer is the one which was pointing specifically here, right? Remember that that's the instruction which hardware was about to execute when the timer interrupt was raised, right? And at this point, essentially, the hardware says, okay, I'm ready. I switched from privilege level 3 to privilege level 0. I switched from executing some user level code here to the entry point of the interrupt handler. I switched the privilege. I'm ready to start executing the entry point of the interrupt handler. Let me stop here for a second. Are there any questions?
So I just want to quickly recap. The interrupt descriptor table, kind of like the page descriptor tables we were talking about a couple weeks ago, is just a list of numbers that point into this section of code, which is where the actual interrupt code is.
Correct. There is a couple of additional fields which are, this is the specific format of this field. So this is an entry in the interrupt descriptor table. What's on the slide is this offset, which composed of 2 parts, because originally it was just 16 bits, but then when they moved to the 30-bit address space, they extended it to 32 bits, right? And this together, all these bits together, is the pointer to vector 32 in our example. This one is the number which chooses the code segment. And this one is the number which is descriptor privilege level. So this will be set to 0, which allows us to transition from privilege level to privilege level 0. And there are some additional fields which I didn't really cover, but they are less important.
Okay, thank you.
One
And,
small question about this entry here. Why do we have two 31-bit entries there? Is that a total of 62 bits or?
yeah, no, like the way it's organized, the first 15 bits are stored here, and the first 16 bits stored here, and the upper 16 bits are stored here. It's kind of legacy, so like logically that's like continuous address, but just the storage has changed over the years.
Okay, yeah.
And this vector 32 is the 32-bit pointer, essentially. Like it just split physically in the interrupt descriptor table.
Gotcha.
And again, we kind of looked at it. So like this is the array. This is how it was. Sorry, like where is it? I thought I had a slide which declares the array. No, maybe I didn't. But essentially, this interrupt descriptor table, I think I did have. Let me just quickly go to the slide. Definition of the interrupt descriptor table. I thought I had it on my slide deck, but maybe I didn't. But the idea is this: it's just an array, and we like this initialization code, which we called from inside the main function, just initializes all elements of the array from 0 to 255, and it sets them all to have a code segment equal to k code, which we configure to have privilege level 0, and for each like for every offset we have an array of vectors. So it's essentially this is the array of function pointers, and we just essentially initializing them, like putting them in the interrupt descriptor table. Question online. Let's take a look. I have a question for you after class. Okay, strange autograder. Yeah. Today, by the way, sorry. Today I will have office hours from 11 till 12. But if you feel like if you don't have time at 11, just hang out on Zoom and I will answer quickly after the class. Okay. Any other questions about the interrupts? About this slide? Okay, now let's take a look at what's inside specifically this vector 32, right? Because it's all nice, we got it. So all of this transition is done by the CPU, right? So you understand that it's the logic of the silicon implemented by the CPU. This fetch, decode, execute loop, right? Essentially, which we discussed earlier in the class. But let's take a look at what has to be here in this vector 32. If I ask you a question, so what do you think you have to put here? How will you implement this interrupt handler? What needs to go inside? If you were the one who codes it. Any ideas? Let's just think of what is necessary, right? So your end goal after the processing after finishing the interrupt processing, you kind of want to come back and keep running the user process, right? Agree? So interrupts are kind of transparent. So even if you context switch from this process to another process on a timer interrupt, you run P2 for a while, and then another timer interrupt comes and you want to switch to this P1, which you were running here originally, you kind of want to continue running P1, right? That's the high level goal. Agree? Or if you do a system call, maybe you want to return to P1 after the system call with some kind of result. In order to do this, we obviously need to restore the state of the process, right? So when you were running here, let me just quickly erase everything on this slide just to make sure that we can clear view. So when you were running here, so imagine you were executing some kind of a move instruction, something in memory pointed by the EAX from the EBX register. Your instruction pointer was pointing here, right? So even in this tiny example, the CPU itself contained the user values of EAX, EBX, all the registers, right? ESP and obviously EAP as well, although it's not like a general register, but it's okay. We still include it here, right? So this interrupt transition really saved only these 5 values. So CPU, if this is the state of the CPU, so the hardware itself save only these 5 things and nothing else. So obviously, the moment you start running vector 32, and especially if you switch to some kind of a C function here, you kind of, before doing that, you need to save all these registers to make sure that when you return from the interrupt, you can restore this state, right? To make sure that after you coming back to user process, this value of EAX and EBX, they are all the same, right? So they are exactly the same as they were when you started processing the interrupt. Does it make sense? Agree? So really, what we need to do in the very first thing in the interrupt handler is to save the state of the CPU. And this is essentially, and then you're free to do whatever. You implement a little bit of assembly, which saves the state, and then you jump to C and you process the timer interrupt. You probably will do something on a timer interrupt. You will do a context switch. So you switch from one process to another. We will cover it later in a class, not today. But you can do anything, right? at this point, you can say, okay, I'm rebooting the system. I don't want to do anything else. But if you want to continue running the process, you have to like save the state of the CPU. And that's what x86 is doing. So let's take a look. So this vector 32, which we use in our example, but interrupts use almost identical vectors. The very first instructions which x86 is doing is first, it says, okay, I will push the error code. You say, like, what does it mean? Like, what do you mean by pushing 0? The reason it's done is that remember that some interrupts, they push an additional value here because some of them, some exceptions, and this value is an error. And meaning that if you say, like, if you say that some of them do push this value and some don't, then the layout of your stack inside the kernel, layout of this stack, is slightly different. For some interrupts, you have an extra field, and for some you don't. And in order to avoid this inconsistency, the software here just says, okay, since the hardware didn't push the error code, we'll just push some dummy error code just to make sure that the stack is organized identically for all interrupts, right? Make sense? Then what it does, the second instruction, it says, okay, by the way, since my goal is to save all the CPU state, I will have one generic function, which it's in x86, it's called all traps. And this function will save and restore the state. But if I blindly go into all traps, I might lose the information about what actual interrupt I'm processing. So in order to remember which interrupt you're currently processing, they push the interrupt number on the stack. So it's currently we're processing interrupt number 32. It's not X, it's just like regular 32. And so they push the interrupt number on the stack just to make sure that we can come back to it, because maybe somewhere later in the code we'll have some kind of a switch which says, okay, based on the int number, if it's a timer, we will do some timer processing code. If it's a system call, we'll do something else, right? So later on, we will like do a switch case on this number, but now we're just pushing it on a stack to make sure that we remember it. And after that, we're just jumping into the all traps. By the way, so you say, look, it's an assembly code. Like, do we have to write it for each interrupt? Well, no. x86 uses a Perl script, this vectors.pl, which is literally just a piece of Perl which automatically generates the assembly file, just kind of like prints it out. And then for each interrupt from like vector 0, vector 1, vector 2, and up to the vector 32, you will have those symbols, meaning that some of them will not push the error code because it will be pushed by the hardware, but most of them will do, right? But it's automatically generated. And I'm not saying that it's the best way to implement it. I would probably prefer to use some kind of a assembly macro and just code it by hand, but x86 people decided that they will use Perl to generate those trampolines by essentially with a Perl script. Okay, so now our stack looks like this, right? So the hardware saved those 5 things here on the stack. The vector 32 pushed 0 as an error code, as a dummy error code, and the number 32 interrupt number on the stack, and the instruction ESP, the kernel stack pointer, points exactly here, right? Make sense? And our call stack in the kernel looks like this. User invoked, or like the hardware invoked interrupt 32, and we're currently executing inside vector 32. The reason I'm so specific about this kernel stack layout, because later on, in order to access the user value, the values of user registers, they will also show up on this stack. So EAX, EBX, and so on will be on this stack. So it's important to understand how to access the user registers, and also the pointer to the user stack will be saved here. And later on, in order to access the arguments for the system call, which user passes on a user stack, so it will be argument 1, argument 2, and so on, we will have to access the value of the user ESP register and then do some math to figure out relatively to this ESP where the other arguments are. So just make sure that those, like, the reason I'm spending time explaining the layout of the stack is because it will become important later. But anyway, so we just have these 7 values on the stack now, right? And we jump to all traps. All traps is the function which essentially saves all the registers. They say, okay, user might have its own value of a data segment, ES segment, FS segment, GS segment. We just push them on a stack one by one. Then we use a specific CPU instruction, push all. And this push all just essentially a single CPU instruction which saves all user registers. So essentially, if you click on this link, you essentially go to the description of the instruction. But really, what happens here is that it just pushes the value of all user registers in this order. So it kind of like implements push EAX, push ECX, and so on, right? So that's fine. Like, we got it. So it's not super hard. So our stack after that will look like that. So essentially, we say all traps will push DS, ES, FS, GS, and all general registers with the push all instructions, right? Make sense? That's the layout of the stack right now. And this stack later in x86 will be called a trap frame. And it will be like, there will be a corresponding struct definition in C, which essentially have all these, like, we will take a look at the definition, but it will have all these registers, EAX, EBX. The layout of this trap frame will match layout of this stack. And you can always access a specific element, a specific value of the stack by saying trap frame equals trap frame EAX will give you the value of the EAX saved by, by this push all instruction. Make sense? Let me stop here for questions.
Just one question, might be repetitive. What's saved in DS, ES, FS, and GS?
No, remember, like, we typically will only talk about code segment. Remember, it's tracks the privilege level, but the data segment and the stack segment, they also say, look, there will be like, all of these will have bounds and bases for, like, all instructions which are relative. Remember, like, for example, CS, some adders, like this logical mode of execution. So CS is always on when you do like any kind of control flow instruction, any fetch from memory. CPU implicitly uses CS. If you do kind of like a move instruction, it will use DS. If you do push pop instructions, you CPU implicitly uses stack segment, right? And essentially, user code is allowed to use other segments like ES, FS, and GS. And in practice, on modern machines, only these FS and GS are used, and they used to implement thread local data structures.
Okay.
Essentially, in order to restore these values, because no, like, you can say in x86 maybe it's not really necessary because x86 doesn't allow user to create anything besides one data segment, but like x86 implements a generic code which saves all this just to illustrate the purpose. They are not really used by x86. The only two segments, the data, okay, the only 3 segments which are used will be CS, DS, and SS.
Gotcha. Yeah.
But those are important because, in fact, if you're very, very careful, if I understand correctly, if you try to do a move instruction, something like move ESP of EAX, I believe it will trigger an exception. It's a nice kind of an extra credit assignment to run it under QEMU and see if it happens. I don't really know myself exactly at this point, but most likely this instruction will trigger an exception. And can anyone guess why?
Is it because it's in the stack pointer is pointing to kernel memory right now?
The stack pointer is pointing to the kernel memory, that's correct. And implicitly, this instruction will be using a data segment, DS. all these instructions are using stack segment, SS. And SS was actually set by the interrupt transition, because remember, we got it from the TSS, and this thing got loaded, this thing got loaded on the CPU. By the DS segment is still kind of a user DS. So it's not pointing to this kernel data. It's still pointing to the user data. Like the stack segment, the one which was in the TSS, will be already pointing to the kernel data, meaning that it like accesses the data with kernel privileges and everything. But DS is not yet set. And this is exactly like what the old traps is doing next. So it will be on my next slide. But what it does is essentially says, okay, let's take a kernel data segment, load it inside the EAX register, and load from the EAX register in the DS and AS segments. So after that, after this instruction, you can start using move instruction without crashing. But all of these are relative to SS. SS was set by the interrupt transition. Code segment was set by the interrupt transition, but this DS was not, and you have to set it manually here. So DS is still pointing to the user segment in a global descriptor table. Make sense? Okay, so
Wenig.
yeah, go ahead. Let me mute you real quick because some people are talking. How is there a way in Zoom to mute everyone? Maybe.
I think there's a mute all option somewhere. I've seen people use it.
So yeah, me too. Mute all. Mute all. Hey. Okay, I muted everyone. Sorry, guys. So then we don't have any chatter in the background. Thank you. Appreciate it. But feel free to unmute and ask a question. So, okay, so this is exactly what happened. So essentially, we did this. So we said, okay, we saved everything, saved all the registers. We're setting up the data and ES segments. We setting, this is a little old, x86 is not using it. This is for per CPU data structures from an older version of x86. It's not used anymore, so don't pay attention right now. But at this point, we say, look, we form this data structure on the, we form the data structure on the stack, but we want to call a function, like the function trap, and it's a C function. The C function takes a pointer to this trap frame as an argument, right? According to the calling convention, if we want to push an argument, we just have to push it on a stack, right? Which means that the trap frame itself sits on a stack. And if we want to push it as an argument, we just like essentially push the pointer to the stack itself, right? On a stack, meaning that this will become the first argument for this specifically trap frame for this trap function. That's what we're doing here. We say, okay, we're going to push the address of the stack on itself, on the stack itself with this push instruction, right? And that essentially allows us to implement the invocation of a trap, of a C trap function passing one argument, which is currently at the very top of the stack, and go into the C, right? So because into the C code, because we don't like, the only reason we use assembly here, because we have to be very careful about constructing the stack frame, essentially making sure that we carefully save all the registers without overwriting the values on the stack. We constructed the code, like the data and the ES segments, and after that, we're ready to jump to C. Okay, got it. So at this point, we invoke C, call trap, and this trap function is a C function, which takes one argument, which we pushed on a stack, right? So does it make sense? Any questions about how we did it? So we land ourselves in the C function, which takes one argument. Remember, calling convention, one argument TF has to be on a stack itself. Agree? That's what we've done. And since the trap frame, the data structure which we're passing, is on the stack itself, this TF points exactly here. Make sense? A little bit of magic, but like, again, a little eye-opening, but not like super jaw-dropping at this point. But at this point, okay, sure, we got it. So we're running inside the C code, right? We don't have to deal with assembly anymore. And essentially this generic trap handler function, as I was advertising earlier, is just a giant switch statement for each interrupt number. And this trap number, remember, we did the push 32, and this trap number field of this trap frame data structure is aligned in such a manner that it specifically points to this 32 number. And we say, okay, if it's a timer interrupt case, it just encodes the number 32. We say, okay, sure. We say we will increment the tick variable only if we're running on CPU 0. Then we acquire some logs and stuff like that. We wake up everyone who was waiting on a timer, because there is a way to sleep in x86. And you keep forward. You say, I don't really want to do anything here. Like later in this function, we say, look, if the process is running and we want to perform a context switch, we go to the yield function. We're not going to talk about it today, but we come back to it later. But at some point, we say, look, like we did the interrupt processing, we incremented the ticks, we woke up everyone who was waiting on a timer. At this point, we can exit back from the interrupt. And the exit back from the interrupt essentially says, okay, sure, since we were inside this function, the normal C function returns. It will obviously return here. Since we pushed on a stack one argument, we say, forget about it on a stack, decrement the, like the stack grows down, right? So if we, like, this is the max address and this is 0. So by adding 4 bytes to the ESP pointer, we kind of throwing away this argument, and our ESP will be pointing right here, right? And this is exactly where we have our trap frame again. Make sense? So, and at this point, we say our goal is to get back to the user. So we have to restore all the values which user had. So we will just fall through into this trap rep label. We saved all the registers with a push all instruction. So there is a symmetric pop all instruction, which just pops all the user registers. We just essentially pop all the segment registers. Since we push 2 additional things on a step, drop number 32 and the error code, which is 0, we again forget about them, adding 8 bytes to the ESP value. ESP will be somewhere here on the kernel stack at this point. And at this point, we are okay to invoke a special instruction, which is called IRAT. The IRAT instruction takes those 5 things which are here on the stack, which were saved by the hardware, and essentially restored the last bits of the CPU, right? So essentially what it will do, it will say, look, there is an instruction pointer saved on the stack. So we will go and essentially load it back into the hardware register. We will have a CS. So there will be like something like EAP here, code segment, E flags, there's 5 values which we've seen before, right? And which, let me just go back here, like these 5 values which were saved by the hardware. And what we're doing here is just this IRAT instruction will take this 5 and restore the last state of the CPU. So the ESP which was saved by the hardware will point back here. The instruction pointer saved by the hardware will point back here to the instruction which we were executing before entering the interrupt. In our example, it was something like move EIX, EBX, right? And code segment will be restored to point to the user code segment. Stack segment will be restored to point to the user data segment. And other segments like ES, FS, GS, and everything will already restored when we were in the trap red assembly code. Make sense? Any questions about it? So IRET is a single instruction which takes these 5 things, and essentially it's kind of like a return from the function, except that return from the function was just taking one value which was saved on the stack, on the very top of the stack, the instruction pointer, and IRET restores these 5.
Just one question in the trap function code. We do check if the CPU ID is 0. Why is that done?
Because like in x86, we'll have multiple CPUs running, and all of these CPUs will be like receiving timer interrupts because all of them will be processing this context switch code, but only one CPU, CPU 0, will be incrementing the ticks, right? To make sure that the time kind of flows linearly. Otherwise, you would have like 4x speed of time. Does it make sense?
Yeah.
Yeah. And the reason it's done because you can do a sleep system call and you say, look, sleep for some amount of time. And essentially, the sleep will add you on a special queue, and this wake up function will be waking you up if you're sleeping on a specific value of ticks.
Okay. But only 0 kind of maintains that.
Yeah, only the first 0 CPU maintains the time.
Okay.
Any other questions? So again, like not super hard. Like let's just again like quickly look at the source code. We started with vector 32, just push 2 values on a stack to make sure that the stack is always aligned, has this 0 error value, has the interrupt number on a stack, number 32. Then we jump to a generic function which saves all the registers. This function all traps. So it's like this. Like here I'm using example of 64 instead of 32. All traps saved everything. After that, we went into the C function, which is called trap, which processes all the interrupts, did something there. And after that, when we're done, we essentially say, okay, we will fall through to the trap ret label, which restores everything symmetrical to this functional traps here. And in the end, we did the IRET. So again, at a high level, it's not super like hard or anything, right? But nevertheless, like it's interesting to see. Someone has a hand. So question, Ali?
So I have a question that does IRET also change the privilege level from 0 to 3?
That's a great question. And yeah, so yeah, it does. Because in fact, this is the whole point. The hardware will blindly follow the protocol. So here on this slide, if this CS points into the entry into the global descriptor table. And technically speaking, you can change CS. Like you entered into the interrupt, and instead of restoring CS to the old value, you can put it to something else. But in normal case, this CS will restore the privilege level, which is encoded by this segment. And essentially, when we're exiting from the interrupt, we again transitioning from the privilege level 0 into privilege level 3, right? That's how it's done. And in fact, the very first time we kind of enter the process, we will configure, like if your main function is here, right? And it's the very first instruction which your user level process will execute, and I can actually guess which instruction it will be, right? So it will be saving push EBP value, right? Because we're maintaining the stack frame. We will configure this kernel stack with the CS value pointing to this user level value in the global descriptor table, and we will do the IRET instruction. And essentially, when we create the process in a kernel, but then we use IRET to exit and start executing the main function. So this instruction pointer will be pointing to the main function and user level, but CS will allow us to switch from privilege level 0 to privilege level 3. Make sense?
Thank you. Yep, got it. Thank you.
Question. Any other questions? All good? Then I will have a tiny little question for everyone. So when we reach this instruction, IRAT, specifically, we are right about to execute IRAT. Let's do a poll real quick. I will ask a question about what is at the very top of the stack. Let me just quickly enable the poll. Yeah, activate it. So go there and answer what is at the very top of the stack. And notice that the top of the stack is the address which is pointed by the stack pointer. The stack grows down, but still we call this the lowest address is the top, right? So I don't know if it's confusing. So let me illustrate it to make sure that we understand it. So on my slides, so if this is the stack, kernel stack, it grows this way, right? So this is the max address, this is the zero address, but we call the value under the ESP is the top. So what's in here?
To clarify, what's in here when we call the IRET instruction, right?
Right, when we're about to call this IRET instruction. And to make sure that it's less confusing for you, here's this trap frame, just to make sure that we understand. But remember that obviously that's how the trap frame was created. But we're about to execute IRAT. See the responses coming. Okay, let's discuss real quick who thinks they are correct and can justify the answer.
So it should be EIP because we've popped all of the information about that in the stack, and the IRET instruction is going to restore the CPU state that was saved before we started executing the interrupt. So that includes all of the segment registers, SS, ESP, E flag, CS, and EIP right on top there, and EIP is on top of the stack at that state.
Correct. So our stack is pointing right here because we already poked all of it, right? And when we are about to execute the IRAT, so instruction pointer is at the very top of the stack. Everyone agrees with this? So the stack was growing this way. This is the address 0.
Could we go back to the slide with the trap return function for a second?
Mm-hmm. This one?
Yeah, this one. So, oh, I see. Okay, so we're restoring all of the segments, the GS, the FS, ES, and all this stuff. And then once we get to the trap number and error code, we're just incrementing the stack pointer so that, or
Yeah.
decrementing, whichever,
Yeah.
so that it goes past it.
Yeah.
Okay, that makes sense. So then, yeah, at that point, then the top of the stack should be EIP, and then the rest of the user state follows. Okay, cool. Just wanted to clarify. Thank you.
Yeah, and the reason, like, there is nothing super kind of like tricky about this question, but still, I just want to make sure that we all can track. Like, the goal here is to be able to kind of reason about it, about the stack, and have it in your mind, and be absolutely 100% clear about how the stack is organized, so you can access various bits of the stack, right? But yeah, you're right. So okay, good. So
Can I ask one more quick question about
yeah,
that?
go for it. Yeah.
I'm assuming we're just incrementing the stack pointer because we don't care about the trap number and error code anymore. Those can just be discarded.
Correct. Yeah. So
Okay.
in practice, in C and in many other languages, you don't zero out the values on a stack, which sometimes can open an opportunity for like a data leakage attack, because you can, like, literally all these values, like all the rest of the trap frame, which was on the stack, it's not really overwritten, so it's still like after you did this like additional things here, you will have like the 32 sitting here and the 0 error value sitting here. Oops, yeah. Sorry, I guess I screwed up the ordering. It's we pushed we pushed 0 first and then 32, and then all this specifically in this other like inverted order, DS, ES values, FS, GS, and all the registers, it's all sitting there, right, in memory. So this is not zeroed, right? So we just simply change the value of the stack pointer. And as you say, we're just simply forgetting about them, roughly speaking, that they are still stored in memory.
Cool. Thank you.
Okay, but IRET obviously expects just the 5 things on the stack, and that's why we have to make sure that the stack is well formed so the IRET works correctly. Otherwise, if you just off by 1 here, then it means that IRET, instead of returning to user level, CS can point to something else, and like you might most likely will just simply crash, right? But this is important to make sure that all the values in the stack layout is exactly as IRET expects it. Okay, so essentially we talked about it. So IRET returned, and IRET itself restores the values of the code segment. This will be the one with privilege level 3, as you just asked. Instruction pointer will point to the user memory, which in our example was executing move EAX, EPX, whatever was executing in user. eFlags was returned, so most likely interrupt flag is again enabled, so it's 1, so we can receive further interrupts. We restore the stack segment and the stack pointer. This will point to the user stack at this point. And essentially at this point, for the user, it's almost like nothing has happened, right? So essentially, like the timer interrupt is completely transparent to the user. Of course, if you're running a tight loop and you're measuring how many iterations of the loop you executed in a unit of time, then yes, you will see the delay because the kernel was executing, right? And obviously it polluted caches, did something. But other than that, from a functional standpoint, it's the same values of the registers. Everything got restored and the user code runs forward, right? Make sense? And okay, so if you ever confused about what's going on, come back to this slide. It kind of like explains what's happening during the interrupt. But let's now take a look at how xvis6 implements system calls. And specifically, remember, the system call is kind of a function invocation from the user. So like kind of like you do a read function, reading the descriptor 0, for example, passing a buffer and a size of this buffer n, right? But in practice, instead of like calling a sysread in a kernel, which implements this function, which implements like a file descriptor, buffer, and the size of a buffer, you cannot call it directly with a call instruction. Instead, what you will do int x40 instruction. And the reason it's done this way, because interrupts, as we already discussed, allow us to, first of all, enter in a controlled manner. So we will enter on a vector. X40 is 64 in DAC. We will enter on vector 64. We'll perform a bunch of checks before implementing the sysread, but also we will be able to switch privilege levels from 3 to 0. So interrupt is one mechanism, and historically it was, I cannot say that it was the only one, but okay, it's one mechanism which allows you to switch from privilege level 3 to 0, kind of implementing this controlled entry in the kernel. And this is how xvis6 does it. So let's take a look. I mean, not surprisingly, so at a high level, the user will invoke this int 64 instruction, right? And that's how it enters into the kernel. It's typically hidden from you by a system library, and I will explain how x86 hides it from you. But on Linux, it's hidden inside the libc, right? And on modern machines, historically, everyone was using int. On Linux, for example, instead of 64, it was int x80, which is 128. So, and sorry, you can, as a system designer, you can pick any number which is above 32, because the first 32 are reserved by Intel, and typically above this you use hardware interrupts for timer and stuff like that. But roughly speaking, any available number can be chosen, right? So it's just design choice which one you choose. And historically, that was the mechanism. It is a little slower and than ideal, and CPU designers said, okay, well, we'll provide you a slightly faster mechanism. So don't get surprised that modern libc and modern operating systems, they don't use an interrupt mechanism, but instead they use a specific CPU instruction, which is called sysenter or syscall on AMD machines. But I'm not going to cover them in this class, but just they work similar. I mean, they have slightly different semantics and everything is slightly different, but as long as if you understand how interrupts work, it kind of will allow you to understand how everything else works as well. So anyway, so x86 uses this vector 64 for entering the user level. And everything happens exactly as you would expect. So user level invokes int 64. Remember that that's the only interrupt which in the interrupt descriptor table was configured with this DPL field equals to 3, which means if you do something like int 65, because this next one will contain 0 here, this is not allowed. That will trigger a protection violation exception. But when we were setting up the interrupt table, we specifically allowed the user to invoke this interrupt, meaning that we say, look, you are running at CPL 3, and the descriptor privilege level here is 3, so it's less or equal, so we are allowing it, right? Cool. Greater or equal, I guess. And so everything is exactly as we just talked before, but instead of vector 32, we land on vector 64. So x86, again, has a bit of assembly code, which pushes the error code, pushes the system call number, now it's 64, obviously, jumps to all traps. Our stack looks exactly like we just discussed. Everything happened as before. So we landed on this all trap function, which saves all the user segment registers, all the user general registers, resets the segments in the kernel, and then it calls trap here. That's the layout of the stack, everything as we just discussed. However, in this giant switch case, roughly speaking, we don't even enter this as the switch case, although it's just a design choice. We say if the trap number equals to the syscall, this is 64, well, we will start processing the syscall. There is a little bit of management code, because if the process is killed, we will clean up process resources. Again, we can talk about it later, but let's concentrate on how we process the system calls. So this function syscall inside the x86 kernel implements processing of system calls. So you got the point. You invoked int64 at user level, you switch into the kernel CPL 0, you saved all the registers like any other interrupt, you're running in a kernel, and the syscall is just a regular kernel function, which now says, okay, look, I will implement a logic of a system call which the user wants to invoke. If you carefully look at this code, you say, like, where is the syscall number? Because this is ours. It's just like to trigger the invocation of any of the system calls. But how will we pass the syscall number into this function syscall? What are your ideas? How would you do this? Like, how do you distinguish between read, write, system calls, exec, fork, whatever you know, any of these? How to pass the value of the system call from the user to the kernel? What are the options?
Can we assign them some number and
Correct.
count number?
We'll assign them a number, like, I don't know, 0, 1, 2, 3. And how will we pass this number? Like, again, I just wanted, you were running in a user, right? Like, you invoked int 64 here. Now you start executing syscall function, which has to dispatch on a syscall number. It has to decide whether it wants to implement a write or a read or something. And imagine we assign them numbers. Write is 0, read is 1. I'm just making up the numbers, but just for example. How do you pass some number, like for example, number 1 from user, from here, from executing here to here? Like, it's not hard. So just come up with it.
You
Yeah, go
could
ahead.
put it in a agreed upon register.
Agree. And so, and this is what x86 is doing. They use register EAX. So in before invoking in64, you say move the value 1 in the EAX register, right? And it's one way to do it. You could say, okay, look, I want to follow the calling convention, and I will push this number on the user stack. And it's totally fine. So those both design choices are possible. You can either pass on the user stack or in some register. And x86 chooses the register, specifically EAX, right? Okay, cool. That's fine. So that's what this function is doing. It says, okay, since we saved the user value of the EAX on the stack, and the stack we can access as a trap frame, and the trap frame is a data structure, which definition just matches the layout of the stack. So then we say for the current process, like, and we save this pointer to the trap frame into the field of the process, the value of the EAX register will contain the number of the syscall. So we get this number, right? And we do a little bit of checks here. We say, look, if the number is greater than 0, and it should be greater than 0, and it should be less than the max number of system calls we support. And by the way, in order to invoke a system call, we maintain them as an array of function pointers. So we say, look, this array value has to be non-zero. We have to initialize it. We just invoke the handler. So it's kind of like in a C++, it would be a virtual method or something like that. In Rust, it would be a trait or something. You can call it an interface if you like, but in C, you can implement it as an array of function pointers. And it doesn't have to be this way. You can like do a giant switch statement here and code everything statically. It's again, it's just a design choice. So just don't be like specific about it, or like, but x86 does an array. So essentially it says, okay, it's an array of function pointers. Let's take a look at how it's organized. So specifically, it's defined as a global variable syscalls. It's array, and each element of the array is a pointer to a function, which returns an int argument, right? By the way, all the functions have voids, right? It's a little mysterious. I'll explain how it works, because each system call has a different number of arguments. So for example, fork has 0 arguments, but read has 3 arguments: file descriptor, buffer, and a size, right? So internally, those functions will fetch those arguments from the user level stack, but in the kernel, they can be all user pointers. They can be all void pointers, right? And specifically in our example, if we do a read system call, this is like the number sysread, right? So this will be passed in the trap frame EAX. So this will be passed in the EAX register, which gets saved on a trap frame, and we can access it like this. Make sense? So here we invoke a function, and we assume, remember, each function, it's a void function, but it returns an integer. And again, the convention is how to pass the argument back to the user. Here they don't break the convention, and similar to any other function, they just return the value in the EAX register. And of course, if we want to pass this value to the user level, well, we cannot just return it in the current EAX value, because EAX will be used in the kernel, will be overwritten. But if we save it on a trap frame, when we will be exiting from the interrupt, this EAX, the trap frame EAX value will be restored by the pop all instruction in the real EAX register, and this register, when we do the IRAT, will be visible to the user later. Make sense? Let me stop here for questions, because I was saying a lot of words, I guess. All clear? And of course, like if we fail this check, we go into this thing and the x86 prints unknown system call, process yada yada. I don't know, like I guess system, like it just returns -1 as an argument to the user instead of crashing the process, but it's again, it's your choice. If the process tries to invoke an unknown system call, you can as well kill it at this point. But whatever, it doesn't matter. Again, your design choice. So anyway, so cool. So we understand how the kernel handles the system calls. But now let's take a quick look at how the user programs invoke the system calls. As I said, okay, I mentioned that in the end, you always invoke int64. But it would be kind of ugly to write this assembly sequence every time we want to invoke a system call. For example, here, in order to invoke exec, sysexec, you have to load exec into the EAX register, invoke int64, stuff like that. But if you like, and push some arguments as well, but okay, don't pay attention to this, right? So how would you hide this kind of mechanical, like, like pushing putting the system call number in the X register and triggering an invocation of a system call in the int instruction? What kind of interface you would export to the user program? In the end, the user program really wants to see just exec like this, right? And that should automatically transition into the kernel. So we need some kind of a tiny trampoline which sets up the X register and does the int64 instruction. But how would you build this plumbing? Do we have an idea? Well, it depends on how. Let me show you one way how x86 does it. So specifically x86 says, okay, we'll have a user.h file, which provides definitions for all system calls, right? And by looking at this definition, the compiler can generate the call site, meaning that it knows that the read system call will need 3 arguments, right? Integer, a void pointer, and an integer for size, right? So this is the file descriptor. That's okay. So if you look at the, like if you compile x86, if you invoke a function, it's an example from the cat.c, so the program which implements the cat logic, it writes into the standard output, right? So file descriptor 1. So for this source line, the compiler will generate this call site invocation. It says, okay, I will end up invoking a write function. I will end up pushing 3 arguments. So this 1 is for this file descriptor 1. It's a constant. In this specific example, the buffer is a static variable, so it's xb00, whatever, just happens to be there. And the size of this buffer or this n variable is in the EBX register. We probably computed the size, right? So this is what compiler generates for the call site. That's fine. So one minor interesting detail, so different versions of GCC with different optimizations can generate slightly different call sites. So don't get confused. So for example, another way I've seen it, so they advance the ESP pointer and instead of using pushes, they use move instructions. So they move 1 into ESP, they move this value into the ESP plus 4, and they move EBX into ESP plus 8. But it's exactly the same, right? Okay, that's clear. So compiler can generate the call site, but still, here I'm just showing but still, where is this int64? How can we get this one running? The way it's done is that x86 uses an assembly file. It's called usys.s. So it's kind of like an analogous to libc in Linux. But essentially what they do is that they rely on assembly macro which essentially defines a global name, global label, kind of like for each of them, for fork, for exit, for wait, for pipe. There will be an assembly file, like what happens here, this name gets replaced with fork here, 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 right? And here, and this stands for concatenation, so it will come out as sys fork. And essentially, it's a tiny assembly sequence which says, okay, I will push the syscall number in the EX register, and I will do this in 64. And after I'm returned from the kernel, I will do just a ret instruction, right? And for each system call, you will use this macro to essentially implement the system call invocation. The reason I'm covering it in this level of detail is because your homework will ask you to add an additional system call, right? And you will have to add an additional macro for whatever this is system call we will be building, some kind of a foo bar, you will have to add it here as well, right? Okay, cool. Any questions about this? So remember, the compiler, when we do this call write, this address is linked with this, like specifically syscall write will declare the sequence with write here, and the compiler will call this label. Does it make sense? Okay, let's assume it does. So, and then it's fine. So that's specifically, this is how this write label looks. If you disassemble the cat.c file or cat.o file, which compiler generates, it literally just, what it does, it just loads the, apparently the write is the number x10, it loads it into the EAX register, and then invokes the interrupt. And this moves us into the kernel through vector 64, right? Makes sense? A couple of other things remain. So we need to figure out how we pass arguments from user level to the system calls, how the kernel can access them, and how we can return the results. So results, we obviously, like an integer result is returned in the EAX register, but maybe like the kernel has to fill in the buffer with data and stuff like that. So let's take a look at how the kernel accesses the arguments passed in a system call invocation. So in this example, when the user invokes write system call passing two arguments, like a pointer to a buffer in user space, and n is the size of this buffer, right? And this is a file descriptor 1. Inside the syswrite, remember, syswrite was a syscall array. This is whatever sys, right? We invoked a function pointer in the array. So this is the void function, right? And it will return an integer. So we will assign it to proc tf eax, right? But in practice, user did pass these three arguments. So where are these three arguments? Who can tell me? How the kernel can access them?
Did you say where are they?
Yeah.
Yeah.
Physically. Which memory? Or where in the program address space those arguments are located?
The stack.
The stack. Which stack?
I think it would start on like the program stack, but I think they get saved into registers on the kernel stack.
Almost. So let me just clarify it for everyone. But yeah, you're right. So if we go back to this interrupt transition slide, so specifically what these arguments, they will be like, if you invoke an int 64, before invoking this, here you move something like move x10 into EAX, and this is the write label, right? Before even doing that, when you were invoking the call side, before you were doing like call of write, you push these arguments, right? You pushed one, you push the address of the buffer, and you push the size n, right? And these three will be on this user stack. There will be somewhere over here on the user stack. Agree? Because you did the call instruction, this write label doesn't really maintain the EBP, right? So the layout of the stack will be somewhat different, but this address of the B00 of the buffer and the size n were pushed on the user stack, right? Agree with this? And later, you mentioned that those will be saved in registers, but really not. Only the pointer to this user stack will be saved as part of the interrupt transition. But by knowing this pointer, the value of the user pointer, and by offsetting into like whatever, there's maybe something else pushed on the stack, like a return address, because we did the call write, right? But essentially, we can access these arguments and buffer address and the number 1, which is the file descriptor. Make sense?
Yeah.
Okay, cool. And that's exactly what xv6 is doing, except that since the user might be malicious and might want to try to crush the kernel, we have to do a set of careful checks, meaning that what if the user, instead of passing this buffer to a user memory, just passes a buffer which points, for example, into the interrupt descriptor table. User maybe somehow guessed the address of the interrupt descriptor table, or passes a pointer into the root of the page table directory, right? Obviously, when we're reading from disk, we don't want the implementation of this file write system call to overwrite any of the kernel memory. That's why xv6, it's kind of like TSA check at the airport. They use a carefully crafted function to fetch the arguments. And so here we see that those functions, for example, they fetch a specific type. So here they check that it fetches a file descriptor as an argument 0 into the local variable f. And if it returns an error, then system call failed because user tries to cheat and tries to essentially maybe passes a file descriptor which is not open. Maybe it's 16 and 16 was never opened. And here they also check argument number 2 into the local variable n, the size of the buffer, and the pointer to the buffer itself is fetched from the argument 1. And it has to be the all n bytes. So you first fetch n, saying, okay, maybe it's 512 bytes, and then you check that this pointer p is fully contained within the user memory, because maybe the user passes n to be like whatever 2 gigabytes, and if you don't check the sizes, then you again maybe spilling into the kernel memory. So let's take a look at how those argument checking functions are implemented. So for example, let's first take if the kernel tries to fetch an integer, right? Integer argument. So essentially what it does here, they say, look, we'll have a helping function, which is a fetch int. It takes the argument number and essentially offsets. So it gets the user stack because it's saved on the trap frame as ESP, right? So it's pushed by the hardware. This 4 stands for the return address because we did call of the write label, but we didn't maintain the stack frame. So there is no EBP saved or anything. So that's why if we try to fetch the nth argument, we just simply multiply it. We do 4 for the call to skip 4 bytes for the return address, and then it's 4 multiplied by n. And we're essentially saying, can we fetch it into the pointer which we provide here? And in order to make sure that those checks pass, xv6 will maintain the current size of the process. Let me show you how it works. Let me show you. So in xv6, the program will be loaded at address 0. We will soon cover the exact system call and the fork system call, so we will know how it works. But essentially, this proc size is the pointer to the max address in user level. Of course, this proc size has to be smaller than the 2 gigabytes because we split the address space into halves. Lower half is for the user, upper half is for the kernel. But roughly speaking, there will be like a process text, process data, we'll create a guard page for the stack, a stack page for the user stack, and then the process heap will be growing dynamically, and it will be tracked by the process proc size variable, right? And that's what this check is doing. It says, okay, we skip the return address, we multiply the nth argument by 4, and now we will be doing this check. We say, look, By the way, the address which we're trying to fetch, this argument which we pass into this helping function, if it's greater than size, then it's immediately a violation because you cannot access the memory above the process size. If you're also passing the size of this, so for the integer value, we say that integer values are size 4, so we check whether you're spilling, essentially trying to pass an integer maybe, which is exactly here on the boundary of it, right? So maybe the first byte is inside, but the other 3 are outside. And that's why we say that address plus 4 has to be also smaller than proc size, right? And if any of this condition is true, you immediately returning because check is not passed. If, however, the check passes, you, since we're accessing the value on the user stack, you're just fetching this value into this provided argument, and you're saying, okay, we fetch the integer, so IP stands for the integer pointer, and that's how the function which fetches the ends argument as an integer pointer. Does this make sense?
Why not? Why not
Yeah.
just have one condition that checks to see that directly checks instead of using the short circuiting or
Great question. Do you know the answer? It's a Google level interview question. So you're saying, why do we need this one and not just this one? Agree? Is that what you're asking? Why not do just add or plus? Can anyone answer?
So you want to check that the first one is at least within the process, like user kernel address space, wherever you are, but you also want to make sure that the next one at least is able to be within the process space. I don't know, that kind of sounded dumb when it came out, but
any other ideas? It's a great question, actually. Every time I teach this class, I'm waiting for this question to be asked. Sometimes I have to bring it back myself. So great thing for asking. But
Wait,
yeah.
is it possibly because of integer overflow?
Correct. Because look, if the user is so tricky that it passes a pointer right here, the pointer is still at the very top of the address space, pointing into the kernel. But if you add, for example, 3, you overflow, and you're pointing right here, so your check will pass, but then the kernel might do something funky here. So it's welcome to C, but it's not just C or not C. It's just the how the address spaces and all the register operations work. Yeah, you can overflow. And in case of a 4 bytes, it's kind of like, it's a little tricky to, like, it's an attack, so the kernel can override the last like 3 bytes of the address space. But imagine if it's a buffer which you pass in a user, and then the buffer might be larger and overflows. And if you only check the end of the buffer that it falls into the user space, some part of this buffer can like provide the access to this memory. Make sense for the checks? Agree? Everyone agrees? So it's kind of clever. And this is one example how modern systems like Linux get exploited. So this is x86 is very, very tiny. It's like roughly 10,000 lines of code. Linux is 24 million lines of code. Imagine how often you have to think about those conditions, thinking that, okay, is it really a legit check or not? It gets hard and people make mistakes. And that's why we have exploits. Okay, let me stop here because I'm running out of, can you please repeat the answer? The answer is that if you just blindly check for the address lat 4, the user value, which is at the very end of the address space. Let me just repeat the figure again. Like imagine you're pointing at the very last byte of the address space. So adder if you just checking for the adder plus 4, adder plus 4 overflows and it points to the 3rd byte here, right? And okay, it's smaller than process size, right? So the check passes. But really, when you start accessing, you will be able to override this last byte. And of course, it's like you can shift by 3 as well if you want. Make sense? Just because the like +4 operation on Intel CPUs will not trigger an exception. It will just blindly overflows. And if you like pass -4 here, then you will overflow into this 0 + 3. Okay, let me stop here, and we might cover really quickly the other checks, but they are kind of self-explanatory at this point, so it's not super hard. But we will quickly finish the system calls. I'm almost there, and we'll move on with constructing the kernel on Tuesday. So I will be in person, so please come. And otherwise, I will assign a quiz as usual, and I will assign a homework. You can start working on it, and have a good weekend. See you guys. Yeah, question.
Sorry, you can end the class, but I do have a question to ask you before you exit the meeting.
Yeah, let me stop recording so it's not going on the not going on record, but man, record. How do I know? How can I stop recording? I have to stop my live stream, I guess. I don't know how to do it. Never